All right, so I know that some of y'all got a test on Monday. Where's Whitener's class? What are you guys doing?
I think we're gonna start central limit theorem today.
Cool. All right, so we're all kind of in the same location. That's good news. Central limit theorem is a big deal, and I know I kind of started talking about it and then we backed up and did some other stuff. Here we are again. The back of the handout that I gave you has the two formulas that for Lang's class, the particular central limit theorem examples that you've done use these two formulas. The one that I gave you a handout for on Wednesday also had a total or a sum formula. That's coming up in Whitener's class more. So we'll switch back to that after we get through Lang stuff first, since that's the test that's Monday. So I put that on the back because we'll be referring to those formulas. If you're like, where the heck is she getting those? That's what those are. So two different scenarios, and I pulled these straight from the textbook, but these are some of the even number ones so that you don't have answers to them. So, you know, if you wanted to do your odds, you still have those for your practice problems. These ones are even. First one, research shows that the curved shell lengths of turtles in the Grand Cayman South Lagoon has a distribution with a mean of 50 centimeters and a standard deviation of 10 centimeters. In the study, 76 green turtles were captured from the lagoon. The mean shell length for the sample was 55.5 centimeters. How likely is it to observe a sample mean of 55.5 centimeters or larger? And I think I wrote CN there because I was typing very fast to make this handout. This should be a CM because it's centimeters. CM, sorry about that. So let's talk through what this is actually saying so that you know whether or not, like when we get to our answer, that it's a reasonable answer or not. So in general, how long should a turtle shell length be according to what this says? 50 is the mean. So if you go pick up a random turtle, it should be somewhere around 50 centimeters is what that says when it says that the distribution has a mean of 50 centimeters, but that's the average turtle you would just go pick up, okay? But they're telling you that they went and they collected this sample of 76 turtles, and they found that from those 76 that they picked up, then they took the mean of those 76, they got 55.5. Is that bigger or smaller than what we thought we would find? Bigger. So the question they're asking you is, how unusual is this? Did you find like the magical 76 turtles in this lagoon that all happen to be the biggest ones? Like, so when they're saying, how likely is it for you to observe a sample mean that's that big or bigger? They're asking you, did you find a weird sample of turtles? Because they said that turtles should have a mean of about 50, but you picked a sample and it was 55.5, way bigger. Which when we're talking about a turtle, that's a big difference. Like, you've got some big turtles here. So what we're trying to figure out is how weird is the sample you just found? Okay, so what we're going to do in terms of this one, this is not asking us about percentages of anything, so it's not a proportion. So in terms of which formula you're going to use, you're going to use the top formula on the sheet, not the bottom formula. The bottom one is for a sample proportion. This one is just sample mean. So using that particular formula, we are going to use our mu is 50. And your standard deviation that they gave you is the 10. Okay. And our sample size, they very nicely laid these all out. That was the 76. And so in terms of your formula, when you need to go figure out how unusual this is, you need to do your z is equal to your sample mean minus the mu that they gave you, divided by, and then this part right here, when we go to do the standard deviation, because what we're talking about is a sample of things, this is where you're going to put the standard deviation. Normally, when we do a z-score, we just put the standard deviation, right? This is a central limit theorem problem where we have a sample of 76. We divide by the square root of whatever that sample size is. That's what makes this different than a normal z-score that we do if we already know the thing is normally distributed like our original problems. This is different. It's a sample. Okay. So we're going to take the sample mean. Our sample mean was the 55.5. So they didn't actually give us that symbol in this problem anywhere. How do I know that that one is the thing that goes here? When they're talking about all turtles in this particular location and they give you the mean, that's going to be the mu. But when they're talking about just those 76 turtles and we went and took the mean, that's the X bar. So we're going to take 55.5, subtract the mu, which is the 50, divide it by 10 over the square root of our 76. Okay, so 55.5 minus 50 divided by 10 over the square root of 76. So I got 4.79. So yeah, I would just leave it at 4.79 for my z-score. All right, before I even go and look at my z table, so this, since this is for Lang's midterm, you guys are using the weird z table. But before I even go and look at the weird z table, what do I know about a z-score of 4.79? Is that a normal z-score or a crazy z-score? So crazy z-score. So normal z-scores are between 0 and 3. And at 3, you're starting to get pretty crazy because when we did with the grades, if you have a z-score of 3, you have an A. You're way out in the A range. Or if you have a z-score of -3, you're way out in my F range. If you have a z-score of 4.79, you're like falling off my graph. You're way out there. So when this is asking how likely is it to observe this sample, I actually, because I already know that my z table, my biggest number that's on my z table is a 4. I'm way the heck off of my z table already. This is very, very, very unlikely. It's so unlikely that it's going to end up being 0%, completely unlikely. How would we end up ultimately doing that? You would be going to as far out as you possibly can on your z table, and the very last row on the 4, because they don't give us 4.79. They stop at 4. 0.5 is as far out as it goes. And then when we're doing these with the weird z table, if we're trying to figure out how likely is it that we're way the heck out here, we're going to be using 0.5 minus 0.5, because from here on over on this side of the table, that's half of the distribution. So we would take the z table score of, we have to kind of, we want 4.79, which is going to be like way over here. And we always start when we're using the weird z table at z is equal to 0. This score from the table, I don't actually have that. I could only go out to the 4. So 0.5 was what it said when I went out to the 4. 0.5 all the way across. It's just going to be 0.5. And this whole side, when I'm going to ask what is the area from the z is equal to 0 out to the entire edge of this whole side of the table is 0.5, or the distribution is what I mean to say. So we're going to take 0.5 and subtract the 0.5 that we got when we went and looked on the table, and we get 0. So in terms of what is my probability, did I actually need the table to do this one? No, because 4.79, I already knew that was crazy. But if you like were wondering, like, what would you be doing if he was like, what does the table show you? What we're basically saying is your number, we went out to 0.5. This whole half of the distribution is 0.5. You take 0.5 and subtract the 0.5, and this is the likelihood, or this is what percent probability it is that you would observe a mean of that. It's basically impossible. It's so unlikely. Now, what they're saying is that this is what you found, though. So it's the likelihood that this happened was basically 0%. So what did you do when you stumbled out on this beach and you found a sample of 76 turtles where that was how big they were? Like, you have found something really extraordinary. And so as like a researcher, you would be reporting on this. You would go, there's a change in the turtles happening over in the lagoon, because it should be 0% likely that I found a sample that had a mean size of shell of 55.5, but I did. So this is the sort of thing where, like, when you're doing the research, knowing that it's basically impossible, but that's what you found, that's when they start publishing papers. They're like, that was crazy. That shouldn't have happened. Okay. What would you probably be doing on an exam? Finding the z-score always. And then usually they're not going to give you a crazy z-score, although if they want you to save time on a test, they might give you something like a 4.79, because you don't even need to bother to take time to go look at a table. You already know that's not likely to happen. It's bigger than 3. Anytime it's bigger than 3, it's pretty darn unlikely to happen. Yes?
Wait, is like central limit theorem like normal distribution?
Central limit theorem, basically what it says is that even though I don't know, because it just says that the lagoon has a distribution with a mean of 50 and a standard deviation of 10, it doesn't say a normal distribution. I don't know if this is normal or not. But I failed to tell you why we could use the central limit theorem on this one. Can you tell me why I was allowed to use the central limit theorem on this one? What was the important number in here? That was it. Did you hear what she said? So, central limit theorem says, even if I don't know if this is a normal distribution, if my sample size is big enough, the distribution of the sample means is going to be normally distributed. And what number did they determine was big enough? 30. So our sample size was 76. So because it's bigger than 30, I was allowed to do this. So you're looking for problems where they're talking about a sample. If that sample is bigger than 30, then I'm allowed to pretend like it is the normal distribution, which means I get to use a z-score. If I didn't know that, if I was not sure about what the distribution was and I didn't have 30, we can't use the z. You guys haven't learned what you can use yet, so most of the problems are going to be more than 30 at this point, because if they're not, you're going to have to say, I actually can't use the central limit theorem. I don't know anything about it. You can use the central limit theorem formula, so you can still use this one if your sample size is under 30, if they say the words in the problem, this is from a normal distribution, but they didn't in this problem. They just said it was from a lagoon that has a distribution with a mean. It didn't say a normal distribution. If it did, then it wouldn't matter if you only found 5 turtles. You're still allowed to use this formula to find the z-score. Okay, so central limit theorem, we actually don't need the distribution to be normal. The sampling distribution will end up being normal as long as we have a sample size of at least 30. How'd that feel? It's words, right? Like some words. Distribution versus the sample distribution was what some of those homework problems were trying to get at, where like we were talking about the dice in the last problem, what I did on Wednesday, only the 3-sided dice, and then we were adding up for all 27 of the different possibilities, and then we found the mean of that sample. That's a sampling distribution versus the overall distribution. So we have an overall distribution that has a mean of 50 and a standard deviation of 10, but they're telling you that this particular sample of 76 turtles is weird. And so it doesn't have the same mean. In fact, its mean is not 50, its mean is 55.5. So it is different. And so that's what's kind of interesting about knowing central limit theorem stuff. Okay. The next one is not the same formula. And here's how you can tell. In this problem, it's talking about percentages of things. Those are going to be sample proportions. So they'll either actually say proportion in the problem, or they'll be talking about percents. So this says, when presented with fingerprints from the same individual, a fingerprint expert will correctly identify a match 92% of the time. Consider a forensic database of 1,000 different pairs of fingerprints where each pair is a match. What proportion of the 1,000 pairs would you expect an expert to correctly identify as a match? Okay. So that second formula over here is, this is going to be your sample proportion. This is the proportion of the overall distribution. And then they have P times 1 minus P divided by N all underneath that square root sign. So the square root is going over the whole dang thing. So even that N is underneath the square root sign. So that's important. I'll show you, like, I'll write it so that it's not all crammed together like that. What is 1 minus P? The same thing is, it's also Q. So they could have written this formula for you with that bottom part right there replaced with a Q. That would be exactly the same formula. So if they say 1 minus P or they say Q, they mean the same thing. Okay. All right, so let's think about this. This one, the first question is saying you have 1,000 pairs of fingerprints. So what proportion of those 1,000 pairs would you expect an expert to correctly identify as a match based on what this says up here? This actually isn't requiring you to do crazy math. This is asking you to read a thing that it says up there. 1,000 pairs, if I actually asked you for the number up here, I would need for this overall to become 92%. Now I'm actually not asking you for the number. I'm just asking you for the proportion. So literally I need you to take 92% and turn it into a decimal. Okay. In terms of notation, this is what is my expected sample proportion. And so we put a little, we call that a hat. When I put that on top of the P hat, expected proportion of P hat, that's the sample proportion. 0.92. So that one didn't actually ask you to do a calculation. It was a reading part of this question. We correctly identify the match 92% of the time, then I expect that the expert is finding the match 92% of the time, but we're turning it into the proportion of 0.92. The second part is where the actual calculation is happening. What is the probability that an expert will correctly identify fewer than 900 of the fingerprint matches? So 900 out of 1,000 fingerprint pairs is what they told us. That's 0.90. So sometimes when they do these types of problems, they switch back and forth between using fractions and using the decimals for the proportions. So don't be scared. We just have to make sure that since we were already talking about a 0.92 before, I want to turn this one into a 0.90 so that I can put it into the formula together. So this is asking, what is the probability, if I write it in that notation, what's the probability that my p hat, that's my sample proportion, is less than 0.90? That's the question we're asking. And in order to answer that question, what I need to do is figure out what's the probability that our z-score is some number. We're going to go find that number using that second formula. Okay. Second formula time. So I'm going to put z is equal to 0.90, that's my p hat, minus the population proportion, that was 0.92, divided by, and then this is the thing where the square root actually goes over this entire fraction I'm about to write. It wants the p, so 0.92, and then it has 1 minus the p, same thing as the q. What's my q going to be here? Yeah, 0.08, because remember p and q together have to add up to 1. So if this is 0.92, then the other thing has to be 0.08. The other way you can do that is just do 1 minus the p, like the way the formula says. And then we're supposed to divide that by our sample size. And they said our sample size is 1,000 for this one. We're going to go find our z now. Okay, I got negative 2.33 if I round it. Okay, so what this is really asking is what is the probability that z is less than negative 2.33? Now, my whitener people, you can use the normal z table I gave you. My Lang people, we have to use the weird z table. And the weird z table only has positive z's on there. So this negative 2.33 is over here. But the table always tells me from z is equal to 0 over to the positive version of that. So that would be positive 2.33. So when I go to the table, it's going to tell me this area right here. Okay, so 2.33 is 0.4901. Okay. But what I want is actually this part of the distribution. So how do I know that's the part that I want? It says, what's the probability that our z is less than negative 2.33? Here's negative 2.33, so less than that is this part. I just want this tiny little part, so I should get a very small decimal when I do that. How am I going to do that? Well, this area right here is the same as this area right here. And so I'm going to take 0.50, which is from here to here. That's all 0.5. And we're going to subtract the area we got from the table, and that's going to give us that little area right there. If you have Whitener's class, you don't have to do that. You literally are just going to go to negative 2.33 on the table, and that will be the right answer, and you're done. So the two tables do different things, and I really like the other table better, but this one we can still do. We're going to take 0.50, and I'm going to go ahead and subtract this area from the table, which was 0.4901. And I got 0.0099. So this says, what is the probability that an expert will correctly identify fewer than 900 of the fingerprint matches? You can leave this as 0.0099, but if they wanted the answer as a percent, you'd move the decimal point over 2 places. This is the same thing as 0.99%. As a percent, 0.99%. I'm going to pop the 0 in front of it so that you don't confuse that as 99%. That's not 99%. That's less than 1%. We have a less than 1% chance that these experts who identify fingerprints are going to get fewer than 900 of them right. It's really unlikely. It's less than 1% chance that they're going to get fewer than 900 of them correct. So very likely they're going to get way more than 900 of them correct. Yes.
Wait, I'm just confused. A and B, because I know in A you wrote like P hat is equal to 0.92, but like in B, P hat was 0.9. Like, does it change?
Oh, wait, I probably did just write the wrong thing here. Let's see. My P hat is supposed to be for my, oh, yeah, you are correct. I messed that up. That should just be your P. Let me make sure notationally. Yeah, that should just be your P. I'm glad you asked that question. That's for my overall population. Yes. Where did I get the 0.50? Are you in Lang's class or are you in Whitener's class? Okay, sorry. So then you do need to know this. I was like, Whitener's people, I'd be like, ignore this. You don't need to know this. Okay, cool. So you need to know that the way your table works, it expects you to use the fact that half of the distribution is 50% of the distribution. That's 0.50. This half of the distribution is also 0.50. So depending on what part of the table they're talking about, we're still talking about half of the distribution. So even though we had a negative z-value, your chart only does positive ones. So when I looked on the chart, I went to positive 2.33, and that's where I got this number right there. That filled in 49.01% of the distribution. See how it's almost all filled in? Just that little tail didn't get filled in. So if I asked you how much of this didn't get filled in, you would say, well, Jen, the whole thing from here on over is 0.50. And from here to here is 0.4901. So if I want that piece, I just have to take 0.5 and subtract that. Does that make sense? Even though I actually want this tail over here, this tail is exactly the same amount of area as that tail. So it's okay that it's actually over here. Your table is just weird. It only ever gives you the positive one, and then you might have to go talk about the other side, but the area part stays the same.
If it's positive, you have to do extra work.
Correct. If it's positive, then I would just say, cool, that's where it got filled in. How much is that? And then you would just say, oh, 0.5 minus that. It's the same calculation though. Still gonna be 0.5 minus that, right? Either way. Why do I draw the little picture? Because I get really confused about the negatives and the positives. So it's helpful for me to have the visual on there of what part. They want the little tail part or they want the big fat part. They wanted their little tail part.
Wait, why do we remove use the little arrow on top of the P for part A.
So there's actually, now that I'm thinking about it, the way they asked this question, here's what I should write. We expect, based on the fact that they told us that this is the case. The problem told us this. Okay, they told us this. And it says, what proportion would we expect it to be? If we expect, just based on what they're telling us, we would expect the P and the P hat to be the same number. We would expect that. So same thing with the turtles in the last problem. If you're just asking me, cool, I know that these turtles in general have a mean of 50 centimeters for the length of their shell. And then I'd say, well, what would you expect when you go pick 76 of them? What do you expect is going to happen? And you'd say, well, I would expect that they would be 50. So we would say we expect X bar would still be 50. The thing is, X bar definitely wasn't 50. X bar was 55.5. But what did we expect was going to happen? It's normal to expect. So actually, in terms of what I expected, leaving the hat there does make sense. But the point that he was making was, well, later when you did the formula, and that was where we were supposed to be putting the P hat, he was like, well, why did you put, if that was P hat, why didn't you put a 0.92 there? And I was like, oh, actually, because P hat is actually not that number, but we expected that number to be that. So this question was just asking, what did you expect? There's a lot of nuance in there. I don't think that that's the kind of question you're going to get for exams in terms of you needing to use the notation on it. I would just say, what would you expect? You'd expect 92% of them, or expected the proportion to be 0.92, and you don't need to put a notation on there probably. How you feeling? You're supposed to make a formula sheet for Monday, right? Do you feel like you have all the things on your formula sheet that you need? Do you want me to ask if someone wants to show their formula sheet and we talk through it and see if anyone has anything that other people didn't include? Do you want to do that? We don't have to. It's just like if you might want to. You have one to volunteer? Okay. Whoa.
It's a little crazy.
Whoa.
I put a lot of examples.
Yes, you did. All right, I'm gonna do like half of this at a time, so you actually have a fighting chance of seeing, because she did such a beautiful job of making everything all fit there.
And you can use the back, but it's just like one thing.
Ooh. Okay, so those of you who made a sheet, did you get down uniform distribution? Having a picture for uniform distribution is a really smart idea, because all of the uniform distribution problems, every single one of them, you should be drawing a rectangle for yourself every time. So one of the questions that we had earlier was a uniform distribution question. When I say earlier, I mean literally before most of you came in the room. And we had this uniform distribution where the smaller number, the A, was 5, and the bigger number, the B, was 70. And the question was, what would be the 67th percentile? For this distribution? If that was the question that you got, would you have any idea how to start it? It's okay if your answer is no. So they've given us a distribution. They said the A is 5 and the B is 70. And what we know is that whenever we're going to do one of these things, if we want a percentile, then they're telling you, if this is your starting place and this is your ending place, this is your 100th percentile if you go all the way across. So 67th percentile means you haven't made it across the entire rectangle. You're maybe like there. That would be like your 67th percentile. Okay. But I actually don't know what that number is. I'll call it a C. I don't know what that C is. And so when they're asking what would be the 67th percentile, they're really asking you in code, what's the C that would get you here on that distribution. So how would you go about doing that? Well, we would want to set up a proportion of just the rectangle in question. I don't have different colored chalk, do I? No. Okay. So we're just going to say, what's the proportion from here to here divided by the whole rectangle's length? Okay. So if I want to know what the whole length on this rectangle is, from 5 to 70, you would say, oh, 70 minus 5, the length of that rectangle is 65. Is that okay? So the length on that rectangle is 65 because I took the 70 and I subtracted the 5. Okay. If I want the length from just here to here, I can't just say number minus 5 because they didn't give us the number. So you have to actually write C minus 5 because I don't know what that number is. And overall, when I take this proportion, I want it to be the 67th percentile. So you're going to change that into a decimal and turn it into 0.67. Is that okay? When I take this and I divide it by this, I should get 0.67 in my calculator. So this becomes an algebra question for you. I'll do the algebra on some paper. So we have C minus 5 divided by, we took 70 minus 5 and that gave me the 65. And I want that to come out to be 0.67. So algebraically, if this makes you feel better, put this side over 1 and then cross multiply. So you would multiply those two things together. 65 times 0.67 is 43.55. And then we put our equal sign down. When you cross multiply, you multiply those two things together, you put your equal sign, and then you multiply these two things together. And 1 times C minus 5 is just C minus 5. And we're trying to figure out what is C. So in terms of your algebra skills now, if I'm like, what is C? What do we have to do? Just add 5. You're almost done. Just add 5 to both sides now. So it's going to be 48.55. So the answer to what is the 67th percentile is 48.55 is the 67th percentile. Now, if you wanted to make sure you did this right, then when I take 48.55 and I subtract 5, I get 43.55. And then we would divide that by the total length, 70 minus 5, which is 65. And when I take 43.55 and I divide it by 65, I better get 0.67 or I did this wrong. Yay, 0.67. So we got the 67th percentile. So it worked. All right.
And this is just for the uniform.
This would only work for your uniform distribution. And so that's why I think it's really good that you put a drawing down for your example, because for uniform distribution, whenever we're drawing the rectangle, this part, I actually might recommend that for this part, you also write that this is also the height. Are you okay if I write the word height under there for you? That's always going to be the height on that rectangle. So when you do the f of x part, which is 1 over b minus a, that's always going to tell you how tall that rectangle is. And then when you want to know how long that rectangle is, you're always taking the biggest number minus the smallest number. So b minus the a. That's going to be the length on the rectangle. Okay. having the formula for the variance of that thing is also really smart, because the variance thing, you're dividing by 12, which is not a number that I would usually remember. For most of the things, you know, we divide by 2 or we divide by n or whatever, but the 12 is, it's always 12 when we're doing the variance on the uniform distribution. So I would have that formula on there. Good question. So what she wrote is perfect. She wrote the variance is this. If you want to write down the standard deviation on your paper, then you would write exactly the same thing, but you'll put a square root over that whole thing. Good question. Yep. So this is perfect because she wrote variance, but if you wrote standard deviation, you would put a square root over that whole thing. Is that okay? So the standard deviation is always the square root of whatever the variance is. Good, good. She put a really smart example on there where it was asking for a probability just between two different numbers. And so because the actual length of the rectangle was 70, but it wants the probability that you're only between 0 and 42, then in the bottom, you're still taking the 70 minus the smallest one. That's where the 65 goes. But they gave you 42. You're going to subtract the smallest one. That's where that 37 came from. Good idea to have an example on there. Okay. Why is the probability that x is equal to 20 0 for this problem? It's actually not outside. You were correct if this had said, what's the probability that x is less than 4? Then because the length of the rectangle is from 5 to 70, 4 is outside that range. But she's saying, what's the probability that x is exactly equal to 20? 20 is actually in the range. But whenever it's an exactly equal to, for probability distributions, exactly equal to, the probability will always be 0 if they put equal to. If they say less than or they say greater than, that's when we actually have interesting numbers like that. But if it's exactly equal to, even if it's in the distribution, it's always going to be 0. That's a good thing to keep in mind. This is actually a calculus answer, but not really a hard calculus answer. When we're doing uniform distribution problems, you're always finding the area of a rectangle, right? And so you have a length times a, or I guess I should say height, a base and a height, or a length and a width. Well, if we're saying what's the probability something is exactly 20, then what they're telling you is that the height on the thing is 20, but if it's exactly 20, what's the width of exactly a single number? And the answer is it doesn't have a width. So we don't have a thing to multiply it by. There's actually no amount of length happening if we're going up to exactly 20. So we'll say we're multiplying by 0. We're not really multiplying by 0, but there's no, when I want to do my base times my height, there's no base. There's only a height. So it ends up being 0 for exactly one number. As long as you have to go over to at least 1, now we have a base of 1 times 20, and we could say it was 20. But because we don't have any width when it's exactly one number, that's why it's 0. And it wouldn't matter what number we said. It didn't have to be 20. It could be 5. It could be 2. It could be 8.5. It's still going to be, if it says exactly equal to, the probability is always 0 because there's no area. Okay. Other things she's got on here. Normal distribution. If we're talking about a standard normal distribution, then you have a mean of 0 and your standard deviation is always 1 if it's the standard normal distribution. In terms of converting things to the standard normal distribution, that is just when you find z-scores. So that's why she has the z calculation there. That's what it means to convert something to the standard normal distribution. Okay. In class together, we did several problems where we took this z formula and we rearranged it so that we got X on one side. So instead of having Z is equal to, we had X is equal to. So if that's something that on a test or a quiz, you'd be too nervous to do that rearranging, it might be smart to have the other version of that written on there too. That will give you it, what, if you have a given percentile, then you can go back and find out what the actual original number was. That's smart. Other things she's got on there, proportions.
That was just from the homework, just in case.
That was the thing that we did together today, and I'm going to change your formula just a little because that's square root of the whole thing. So that was like our example problem that we did with the fingerprinting. That was this formula. She wrote the Q instead of P times 1 minus P. It's exactly the same formula though. And then she put an example that's different than the one that I did, but same thing, good idea to put an example, or you can put the fingerprint problem example if you want one. Okay. How to understand the table. Those of you who are in Lane's class, if that's something you'll freak out about, might be smart to have a little piece on how to understand the table. And if you want to go back to my video from Wednesday, I have those examples in there. You could copy those into your notes. That'd be smart. And sampling distribution, that was also an example problem that we did on Wednesday. If that's something that might freak you out, there were lots of steps to that. How is it the entire period for this thing? So I guess he could ask you to do that in that amount of time. That would take most of the time though. Right.
With that one, that one's for the discussion.
Yeah, good reminders on what those signs mean. That's smart.
Yeah.
And to get the mean and the variance, these are specific to your, when you have the sample for that particular
It's for
distribution.
that one.
Yeah, it's for that part up there.
Yeah.
Cool. Well, thanks for letting me show people that. Okay. You're gonna do fine. You want to make sure though, if you get nervous, have some example problems for yourself on the sheet, because sometimes I blank out when I get on an exam, and having something to go back and review and be like, oh yeah, it looks like this one is a nice thing to match. Try and get some sleep this weekend. Everyone looks really super tired. And also, if you got a